media
can we start the difference of
Are you ready, media? Take it now. Wait, let me introduce you.
Will you be speaking intermittently?
No, I will be.
Speak on another mic.
Do you have another mic? How can you off?
So whatever you say will be.
I will be. Give it. For this session, no, and is to start better. Thank you very much. Remember, yes, ma'am. Yes, ma'am. Okay. To do ourselves, we are not here to say, oh, this is so bad or this is so. We are to build ourselves. Any area that you think you are not convinced or you feel you want to ask questions, you have the right to ask. If the time finally elapsed, the time we give for the question, if it's gone, the contact of the person will be displayed, then we can continue our interaction. I think it's not better like that. This place is not, even if I make mistake in my spoken English, I make mistake in my presentation, we are family members giving ourselves so that to think we have a stronger statistical family. Thank you very much. All right. The session chairman, professors here present, and ladies and gentlemen, good afternoon, everyone. My name is Mecca Fortune. I'm here to present a paper titled A Parameterized Extension of Exponential Discriminant Analysis for Enhanced Classification. Exponential discriminant analysis has emerged a powerful technique in scenarios involving high dimensional data. No, I'm okay. In scenarios involving high dimensional data, the traditional exponential discriminant analysis is an extension of the linear discriminant analysis. It leverages the exponential function to bypass what we call singularity problem in some data types. And so what we did in our work is to employ the EDA and also to enhance the EDA via introduction of parameters A and K that were not there. The original exponential function is just e to the power of x. And the introduction of those parameters will enable us to control the exponential growth. And by so doing, we intend to achieve better group separation or better classification accuracy, which is the goal in classification. And so, by way of introduction, discriminant analysis is classified into linear discriminant analysis, and we have quadratic discriminant analysis, depending on whether what we call the covariance matrix, if it is homogeneous or if it is heterogeneous. If the covariance matrix is homogeneous, we look at linear. If it's heterogeneous, that means unequal, we look at quadratic discriminant analysis. Now, the linear discriminant analysis is further classified into predictive discriminant analysis and descriptive discriminant analysis, depending on if we are interested in classifying individuals into already existing groups, that's predictive, or we are interested in picking out variables that are responsible for group separation, that's descriptive discriminant analysis. And so in previous studies, with the target of bypassing what we call cost of dimensionality, an issue that happens in high dimensional data, whereby the number of features exceeds the number of samples. So whenever we have that kind of scenario, there's the possibility of arriving at the singularity problem. And in linear discriminant analysis, there's what we are supposed to do. We are supposed to, in our solving, take the inverse of what we call the within class scatter matrix. And when the within class scatter matrix becomes singular, then we cannot take the inverse, and linear discriminant analysis will fail. And so because of that failure, the exponential discriminant analysis was proposed. Now, the exponential is an ever semi positive definite matrix, the exponential function. By so doing, it bypasses the problem of singularity. And so the exponential discriminant analysis now does better than the linear discriminant analysis. But in our work, we looked at enhancing that exponential discriminant analysis by bringing in parameters into the exponential part of the function. Now, the exponential part of the function is the scatter matrices. So the equation 1 that we have is the Fisher discriminant criterion. This equation, the numbering, I adjusted it here, though we're using the older one that I sent to them. I didn't notice there. So equation 1 there, the within class scatter matrix is the one under, that's SW. SB stands for between class scatter matrix. And then W is called the discriminant criterion that we intend to, that's W is the optimal projection vector. So the interest is to solve for that W. And then that equation JW will maximize that equation. When we maximize that equation, we achieve enhanced group separation. So by so doing, the scatter matrix, we define it with equation 2. And then we'll have the mean there, that's the group mean. And then if we go on to equation 4 and 5, we'll see the within class scatter matrix and the between class scatter matrix. And then to solve for W, ultimately we arrive at W when we get to equation 7. So if we have the value of W, then we'll maximize JW, that's the overall target in linear discriminant analysis. But in exponential discriminant analysis, we employ the exponential function. That's like a Taylor series expansion. From this description under here, every matrix exponential has an inverse, because we see that exponential minus a times exponential a can be written as exponential a minus a, which is I. That's to say that exponential minus a is the inverse of exponential a. And so the exponential discriminant analysis leverages on this exponential property to bypass the problem of singularity. And so that makes it better than the original LDA, which is the linear discriminant analysis. So we have the LDA function given in equation 8, and we have the exponential discriminant analysis given in equation 10. The basic thing is to take the exponential of the scatter matrices. So when we take the exponential of SV and exponential of SW, then we achieve better separation. But if we go on now, so these are the steps. We have the steps to follow when we are carrying out the exponential discriminant analysis. So first is to compute the scatter matrices and take their exponentials. And then next is to find the eigenvectors and the eigenvalues. And then we sort the eigenvectors according to the eigenvalues in decreasing order. And then we orthogonalize to avoid overlap of the, we orthogonalize the columns of the projection matrix. So in our work, instead of just taking the exponential, we brought about bringing in parameters to see how it will bring about better classification. And so in equation 3.3, we see a theorem there. Sorry, in 3.3, we have a theorem there that we kind of use to justify our method. And so if we have a function a exponential kx, as a is greater than 0, and we have s greater than 0, it's possible to have a exponential kx greater than exponential x. And then this is further emphasized in this graph. The graph here gives us a picture of how the curve changes, the exponential curve changes whenever we vary numbers. If we bring in coefficients to the
Is to optimize the curve. What you are going to do is to optimize. That is the final your final task when it comes to ROSM. Then in LLRO, we are not interested in studying whether the parameters lie in a particular interval or not. we are not interested in that one because for LLRO, unlike OLS, where you have one set of parameters, estimated coefficient for all the what's it called, the data points. In LLRO, you have different set of parameters. If you have, for instance, 6 data points, you have different set of parameters for data point 1, data point 2, data point 3, and so on and so forth. So in that case, there's no way you are going to begin to analyze the shape or where the confidence where the parameters lies, so to speak. Please, next page. Then question 3 is the mathematical representation of our LLRO. You see that it is almost the same with the OLS. The only difference here is the inclusion of the W subscript I, which are actually the weights. So okay, so here this is the description of the weights. You look at it now, W11 and so on and so forth. They are different. Please, next page. Then this is where we derive the Penne weights. This is where we derive it. If you look at it very well, you discover that it is a decreasing function. Okay, please next. Then to determine the value, the optimal value of your B, you use this criterion. We call it a penalized press criterion. Then limitation of LLRO. We discovered that in spite of the prospect of LLRO, if you still compare it with the performance of OLS, you still discover that the difference in the performance is not much. In fact, in some cases, the OLS will perform better when you apply LLRO to studies that involves just small samples. If we just small samples and the study that involves more than one explanatory variable. If it is one explanatory variable and the sample size is very, very large, LLRO will perform better. But in OSM, we deal with small sample. We deal with small sample, and again, we also deal with studies that involve more than 2, 3, in some cases 4 explanatory variable. That is independent variable. So what we did in this work was to see how we can make LLRO to perform better than the way it is presently. Please, next page. Okay, sir. So yeah, please go to the next page. So like I said in my introduction, I said what motivated our work was that if the kernel weights are similar, you are going to get a very poor performance from LRO. But if they are different, they are distinct, that is the variability. If it is high, you get very high performance. So what motivated the work was that, okay, fine, how do we now increase the variance of the kernel weight that we derive from Gaussian kernel function? How do we increase it? Please, next page. Next page. Yes, I said therefore the aim of this paper is to modify the GKF such that the general kernel weight matches are of larger variance so as to address the poor goodness of fit of LLR. Please, next page. Please, next page. Next page. Okay, so we started from, this is our derivation. Started from equation 11, then from equation 11, we try to expand equation 11. You know that we try to expand it by multiplying to get equation 12. Then we collected lightens in the equation 13, and in order to remove the exponential, we introduce the natural log to remove the exponential, so that our computation will be very, very simplified. Please, next page. Then we continue with this computation. In equation 16, we'll have equation 16 will have we collected lightens. Equation 17 and 18. Then we have equation 18 and 19. Light terms. Okay, then equation 19, please go. Can't see what is there. Okay. But at the end of the day, this is what we got. Equation 22 is what we got. Now, if you look at that equation 22, if you equate A1 and A2 to 1, you will get the original, you will get the variance for the existing GKF. If you equate them to 1, then please go. Okay, here is actually my equation 24. Now, this is the final equation. If you look at it, how do we make the variance of the kernel weight to be as high variable? How do we do it? We said, okay, if we take A2 square to be 1, then you have to get a value of A1 square as high as possible, so that the variance that you get, because that is the equation 24 is the variance, such that the variance you get will be as high as possible. Please, next page. Then we now said, based on the aim of the current paper, the step to ensure that we get a GKF that has high variance as possible. That is what we get. I said step 1, set A2 equals to 1. Then step 2, then you now find the optimal value of B within the range 0 to 1, then A1 between 0 to 1 too, in order to increase the variance of the existing. Okay, sir. Please let me just discuss the results, sir. 1 minute. Okay, sorry. Okay, these are the results. This is the problem. It's a multi-response problem. Please go. Okay, this is the results. If you look at the result, you discover that the performance of LLRO is better across the 4 responses that are involved in the problem that we try to solve. LLRO goodness of it are better in terms of SSE, in terms of arrow square, and in terms of the prediction error sum of squares. Please, next page. So this is the plot of the model residual for Y2. You discover that the residuals for LLRO closer to the 0 line and the OLS, and the LLRO that uses the existing kernel weight. Yes. So the conclusion is that if we adopt our recommendation, the final GKF that we got in 24, if we adopt it, if we apply it, we'll get results that are better than both OLS and the LLRO that uses existing GKF version. Thank you.
Thank you, Dr. John,
Thank you, sir.
for the presentation. It's very, very well explained, and I was following. But my worry is that you were not looking at high variance. I'm not getting it clear.
Okay,
I will
sir.
not try to reduce the variance or whatever.
Okay, sir.
Hold on. Then again, your error, that graph,
Yes.
I don't think it's necessary. There's a condition of your error term, mean 0, a constant variance. Why don't you use that simple statistics? To do the yes. You don't need to plot those it's not necessary. You understand?
Okay, Prof.
Uncorrelated error is just enough. Check with even though it's uncorrelated. That's just all.
Okay.
So
Please
that
let me. Okay, sir.
that's it. Yeah.
Let me respond, sir. Okay. Okay. So
Is someone else? Yes, number two. Try the other question. Okay. Okay. I'm always probably Tari. So I don't call you Tari.
Okay, thank you. My name is Amechi Ikweze. Yeah.
Amechi Ikweze is one of the repertoire. And we are also allowed to ask questions. So that is why. Thank you very much.
Yeah, thank you. Because your modified model is coming from OLS. I want to ask, does those assumptions of OLS still hold in this your model?
So, any other question? My friend, Dr. Tari. Thank you very much, Dr. Johnway. Um, my concern is around the variance which you hammered on seriously in your motivation. Um, it is not really clear what you were trying to look at with the variance when you were discussing the motivation.
okay.
So at some point you are saying the variance being equal with that of OLS, and then some point you are saying variability of the variance, and then at some point you are talking of high variance. It is not really clear what you are looking at. I don't know if in your paper you have used all of these things interchangeably. Now, the other thing Prof mentioned is that we know for OLS, if the model is fine and okay, the variance should be the minimum. Now, how are you now comparing a variance that is high with an ideal model that is minimum? So if the OLS is ideal, like you even said, I think there is no point talking of the Gaussian kernel weighted something. So it will be fine if you go back and look at this paper thoroughly again to address the issues around the variance comparison. Thank you.
Okay.
Thanks very much. Those are the three. Raise your hand. We are very glad on paper.
Okay.
Please, accept the like our dear friend. Those doctors
Basa. Okay. Okay, Prof.
like that.
Okay, Prof. Okay, Prof. Okay. 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 I'm sorry that I wasn't able to explain why the use of variance. Variance in this case, I try to explain that your uh, Kene matrix, the weight matrix, if the diagonal matrix is a n by n diagonal matrix, the Kene matrix, if the diagonal elements, if they are the same, let's say 0.8, 0.8, 0.8, the performance that you are going to get from that LLR is going to be poor. In fact, it's going to be as comparable to OLS. There's no difference. Please, so the context under which we use variance here is we are trying to look at the variability. We want to get a kernel weight that can give us kernel weight that are as varied or as variable as possible. One kernel weight different from the other n minus one kernel weight. I don't know if I'm making sense. So it is on that it is on that context, the kernel weight, the what why he introduced variance, but that okay, now how do we want to vary, we want to make sure the kernel weight are as varied as possible. So what measure should we take? We decide to take variance. We should have taken something like range, since range is also an example of a measure of dispersion. Why variance? Okay, why variance is I want to I have I have 10 I have 10 kernel weights. I want them to vary. I want them to vary as much as possible, because if they vary, they will be able to address the local differences in the data points. You understand? Because if you look at the examples that we saw, we have 17 data points from that example. If I get a kernel weight that contains the same kernel, if I get a matrix and weight matrix that contains the same kernel weight, I will get a very poor LNR. There's no point. Do I now vary the kernel weight? So each of the kernel weight is addressing the peculiarity, inherent variability, the data points. So how do I, if I basically from the assumption of LNRO itself, I did include the different assumptions. The only assumption I made instead of using the full, we'll still get something that is yes. If you use global kernel, all the kernel are the same. We call it global. So you will still get optimal, but the optimal will not be good enough. So here we put variable kernel weights. Okay, let's put it that way. Variable kernel weights contained inside the matrix, the weight matrix. Because if you don't vary it, the LLR is going to treat the inherent variability in all the data points as the same. It's not going to discriminate against any of them. Yes. Yes. No, it's data. This is data driven, sir. Sir.
I want to just go into data collection aspect of it. Is the data that you collect, the data you have, you are not the one generating it yourself. It is what you get out there as your data. That's what you're going to look into.
Yes.
Okay, so you now trying to like balance, make sure that it's not going, you are going through with your own what you bought in.
LLR.
It can't.
No, ma. No, ma. It's
I want to know how it works because I'm going to
I
use
can
that for my data and see.
okay, ma. Now the data that we collect, the data that we use here, I'm not the one that generated, but I can still generate. I can see I can still generate my own data. I can go to the lab and generate my own data, or I can go to the field and generate my own data. I miss. I apply. Okay, okay. Thank you, sir. Thank you, sir. Thank you, sir. Thank you. Well done, sir. Thank you so much. Oh, sorry, sorry, sir. Sorry. Okay, sorry. Okay. Thank you, sir. visualization mode. We are going to listen to an excellent generalized estimator of population mean in two phases of other rounding unit. So your first half number, right? Please, John, we
variables. When we state this, when you follow these statements clearly, we can clearly see that the expectations of each of these small error terms are equals to 0. Their respective expectation of the squares and covariances I have clearly expressed on the slide. When you move further, we have using so we are going to be doing the proof for both cases. So picking the first case of the for the match portion, that is given C star subscript PM into the expression. I didn't remember to label it, but I had previously labeled it as equation 29. So when we start with this first estimator for the match portion, expressing it in terms of the E terms that we have predefined, when we bring those E terms into it, we have this expression beneath it. When we assume that the absolute value of E permits me to use E, but these are small error terms. When we use the absolute value of E1, the absolute value of E3 plus E4 all over 2, when we assume these respective absolute values are less than or equal to 1, then we are free to use the Taylor series expansions on the respective terms 1 plus E1 all inverse, and also on this other term 1 plus E3 plus E4 all over 2 all inverse. So when we do the Taylor series expansion on each of these terms, assuming terms that are of order 2 to be negligible, we substitute if values, we simplify, and we have our mean square, our biasness as stated in equation 34. And then when we assume that n is large, that the finite population correction is ignored, we have this bias re-expressed as 35. We have the mean square error, which is the expectation of the square of the deviation from the real value stated in equation 36, finally re-expressed in equation 37, and then simplified further in equation 38, and can be rewritten as equation 39 when the partial derivative is taken with respect to alpha 1, alpha 2 star. We have optimum values for alpha 1, alpha 2 star given as 40 and 41. When these values are resubstituted into the mean square error, we have equation 42. When this, okay, we have equation 42 where obviously F star, A star, B star, C star, D star, E star, F prime, Fn, Fm, Fn prime are respectively stated on the slide. Similarly, when we do the same for the other estimator under the unmatched portion, like we have stated in equation 43, expressing it in terms of the E terms with equation 44, using Taylor series expansion on those inverse terms, we substitute and have equation 45. Simplifying equation 45, we have the bias expression in equation 46. If n is assumed large, that the finite population correction is ignored, we have equation 47. And then in the same manner, we have the expression for the mean square error, that is the expectation of the square of the deviation of this estimator from the true population value. We have equation 48. When this is simplified, we have 49. If n is assumed large, that finite population correction is ignored, we have equation 50. And equation 50 can be rewritten as equation 50 when you take the partial derivative with respect to alpha 1, alpha 2, sorry, with respect to alpha 3, alpha 4, we have equations 53 and equation 50, equation 52 and equation 53. When we substitute back, we have the minimum mean square error of the estimator for the unmatched portion stated in equation 54 with every other unknown parameter clearly expressed there. When we bring it back into the optimum mean square expression of the combined estimator, we have equation 58. And when 58, take it back, when 58 is simplified, we have equation 59. And that gives us our proposed estimator, which is a linear combination of two other proposed estimator for both the match and the unmatched portion. So we carried out a comparison, an efficiency comparison with respect to 9 other estimators, the Sine and Khalid's estimator, the Bassett estimator, which are obviously generalized estimator that were broken into several other parts. That gives us 9 estimators. And then clearly, when you move further to see our simulated data that we used to validate our result using Arrow software statistical analysis, we have these results. Now, on a normal day, when we do successive sampling, if you check what they do in textbooks, normally they will determine the optimum fraction of the sample to be drawn in the second occasion. But in our own case, we have been able to do it for different values of this optimum sample to see the behavior. And so when we did that also for different proportional percentages of random non-response in the second occasion, we have the behavior that clearly 2 things were stated. One is that as the sample size in the second occasion is reducing, the estimator is getting better. And also as the proportion of random non-response is also increasing, the estimator is getting better compared to every other case that was considered. So conclusively, that brings us to the end of our presentation. So finally, we have been able to generate an efficient generalized estimation procedure that we called the ratio regression exponential estimator using 2-phase successive sampling under random non-response, which has actually behaved better than several other estimators and is also cost efficient. And I can as well say that it is a robust estimator. Thank you very much. These are my references.
Your full name is Agbebia or Sheikh.
Agbebia. That's why there's a comma.
Agbebia. Thank you very much. Let's suggest that we are heads for Madam Agbebia, who spoke of an efficient generalized estimation of population need to face successive sampling under random non-response. We have questions. Please, before we ask question, Professor Wabweze has an information for men who are members of Cison and who are also the
Good afternoon, ma'am.
The corner that we call women in Cison. Of course, are registered. So many of us are registered women statisticians or Cison members. Yes, we have such a corner, and of course, the beauty in it is that you find out that now women are being encouraged to go into these areas, what we call STEM. And it's you and I that will really have to foster it. Tell people upcoming ones in secondary school, all of us practicing statistics. We're not talking about people that study statistics. You may not have studied statistics in the university, but you practice statistics in one way or the other. If you're in economics, accountancy, medicine, and climate. The inaugural lecture I gave a while ago, I titled the statistics a friend of all. You find out that every aspect, the nutrition is practicing statistics. So let's encourage women. And like I tell ourselves, you see, when women go into anything, including statistics, including practicing and studying statistics, we do better than men, don't we? So don't laugh. We do better than men. Yes, because of the way God has, made us. You know, we designed us. We are more patient. We are more, enduring. Because of course you find out that statistics or mathematical sciences need endurance, and we have it from above, not here. So please, I encourage all of us. There's a paper that is being passed around. If you're a registered member, good and fine, you indicate. If you're not, please come along with us and God will help us. Thank you so much. Thank you.
Thank you very much.
Thank you so much.
For questions, comments, and suggestions. Say what you have. So I'm starting from my friend here. I encourage everybody, please participate. It is you are in your family meeting. What is the silence? You are in your family meeting. Yes.
Yes, sir.
After he said, Harry,
And that question, that is
When is a non-response said to be random and non-random? What's the difference? Secondly, I saw you in your result, you presented a table where you said the non-response was increasing as something was happening. How did you get that number for random non-responses? Thank you.
Okay. So for your first question, the difference between non-response and random non-response. So non-response generally, that's what I'm saying. It's the same thing as just yeah, let me just say it. So non-random non-response is when non-response is not random as the name implies. So is basically, I can put it as when non-response is attributed to the variable or the characteristic of the variable under investigation. For instance, if I'm studying income, let me say standard of living, or I don't know how to put it, of family or households. So that is the variable under study. So if I come to a particular household and I'm not able to get response, it will be attributed that it is because that family is poor. Maybe that is why they did not want to give me information. So it is attributed to the variable under study, income, right? Right? But in random, it is not the case. It could be any other thing that is not related to the variable under study. For instance, it could be that there was a problem with with the safer, or maybe there was a misplacement of questionnaire. Information has been gotten already, but maybe from the side of the person who administered the interview, he misplaced the information, or maybe it was an online investigation and then there was a crash that wasn't the fault of the person who interviewed or the person who gave the information. So it is random in that context. It is independent of the variable as well as every other characteristic that is related to the variable under study. So that is it. The percentages are used. I feel like it doesn't have to, there shouldn't really be a fixed value for it. So you can decide to pick any value, just give it a pattern. And the essence is that you want to see the behavior, either when it is increasing or decreasing. But you could as well look from existing work that have been done from existing literatures. But you can as well just generally see the pattern, provided it is moving in a particular pattern. So that was what I did. I didn't get you, Prof. It was done using simulation, artificially generated. Yes, sir.
Um, your estimator, you did say that it improves when the sample size decreases. Is that correct?
Yes, yes.
And then the other thing is that in sampling theory, estimators tend to improve with increasing sample size.
Okay,
And now your own is giving us the opposite.
okay,
Do you think that there is something that
okay,
needs to be worked on?
okay. Let me explain that.
Thank
On
you.
a normal day, from the law of large numbers, we know that the rule is that when the sample size increases, your estimator is supposed to tend closer to your true value, right? That one is very true. But the case here is this. This is two-phase, two occasion. So when I talk about the sample size here is the picture. The sample size that I'm talking about with respect to reduction in this case is the sample size that has to be drawn in the second phase, because you have drawn your first sample from your first occasion. So you came back, you took a portion from the first part into the second location, and you're supposed to add a fresh sample to it. So it is wisdom for you to determine an optimal value that would optimize efficiency or that would increase efficiency, right? So on a normal day, that value was supposed to be determined, right? But since I did not do that, you can as well look at it from the perspective of, okay, what could be the behavior if this value is either increasing or decreasing? You can as well decide to want to change the value. But what I did for when, why I chose to do for when the sample is decreasing is because we want to also minimize costs, right? So that is it. So you can decide to want to use it for increasing sample sizes as well.
Like that was first. There's a point. What I'm not going to decide on one aspect. Thank you for the presentation.
Thank you, sir.
So I want to have a thorough look at it. Because the solution of that error, I just saw it now. What is it called? It's relative error, not error per se.
Okay, that's relative.
Yes.
The difference all over. Yes, the population value.
Numerator, it post absolute value there. And check. Do your algebra again. Check.
Now, ask your question very well, sir. I'm not getting
Post
it.
error. If they can bring the slide, bring
I
it.
get what the E1,
Yeah, precisely.
Yes.
Yes. It's very important. So that
That's why I said there are small errors. It could be
it's relative error. Go back.
it's relative errors,
Beautiful.
but very
Because
small errors too. Okay.
Relative error is defined in terms of the absolute value and numerator. Because
Okay.
those your what is it called? Variable, they are positive. So, but the numerator may not necessarily be positive when you take the difference. So, in post,
There was a point where we knew that okay, negative value was just be going.
It's very important so that
Proposed estimator. There was a point.
E1, E2, but it was not number. I was not able to capture the goal.
Oh, just keep going. Keep going. Okay, here, go back.
Go back small.
So
You can see it now. The denominator through the positive quantity.
yes.
Beautiful, but that denominator cannot guarantee
Okay.
that's a
For
positive quantity.
cases where we are supposed to get negative values, we had indicated, like when we were going to do the Taylor series, because there was going to be an effect of the negative value.
Because of this algebra you presented. They are relative errors. It's not an error per se anymore. Is that okay? Yeah, look at it. It's not, yes. This research work. Look at this one and see. Wow. I changed the right now. Can you have better results? No, that's right. God bless you. Thank you. As we are in a family, and when you're in a family, you're very free so that suggestions, redirections, modifications, expansion. So we should all work together. All that you are, okay, anybody want to take see, it's very important. Some of these things have to ponder on them. You direct yourself, and then what pictures can even come out because of what is that it's when you are landlocked, when you decide to seal your hands and go away. This one not in the treasure. It's the way papers will now also be in the deadlock. So thank you very much.
Agbebia. Yes, sir. Thank you, sir.
Person I want to present on the Professor Lusa is not good. It's not good.
Yes. I see the get someone in that. You know that this one is very important that's confusing me. If I touch here, it will affect here. But this thing, try and reduce it small, please. It's putting your paper. Mm-hmm. Yeah, dinner now. But it's still 14.
Thank you.
Yeah, no, it's sweet. It's like this.
We are trying to bring it up.
Yes, sir. No, but, more than you. This is
Okay. Good afternoon, everybody. Good afternoon, everybody. My name is E.Osemwenkha. I'm here to present a paper titled A Compound Distribution for Model District Failure Events. Generally, classic district distribution are normally used to model reliability and survival events. But one unique thing about this district distribution is that their parameter are always assumed to be constant. In other words, if you have a case in point, the binomial distribution where you have a p, so for all you know values or outcomes, it has that particular assumed value of p that we use it to consider so many other probability of that particular event. And another thing is that this district distribution has been applied in survival and reliability analysis. But the question is, what can we say if such district parameters are no longer constant? Can we make a probability statement about its nature? Now, so many authors, researchers, have considered these circumstances. In the case of binomial, Cison, and binomial distribution, where they consider the parameter of a Poisson distribution following a beta distribution, and that of where they consider the parameter of where they consider parameter of binomial distribution to follow beta distribution, of Poisson distribution to follow gamma distribution. So in our own case, we are considering uh, geometric distribution, and the geometric distribution is starting to be and we are trying to consider the parameter of the geometric distribution to follow a standard power distribution and see what we can obtain from that. So we considered a failure event for the geometric distribution, which is given by equation 1, and in equation 1 follows the standard power function distribution, which is also given by equation 2, and these two variables are assumed to be what? To be independent. In other words, the joint distribution of x and go on. the joint distribution of X and P will give us equation 4. But in other words, the expected value of P, which follows the exponential distribution, is given by 3. You know, I'm just trying to characterize that of the standard power distribution. So if we have the joint density function of X and P, then integrating with respect to, if we are integrating out P from equation 4, we have the resultant or the marginal distribution, which is given as equation 5. And this marginal distribution is what we regarded as the new compound distribution. And we called it to be what? To be geometric standard power function. Now, and the corresponding the cumulative density function of equation 5 is given as that, which is the probability that the sum of x is less than or equal to small letter x. Now we try to plot the graph of equation 4, considering the various parameters, the varying parameter of the model, and we notice that follows monotony decreasing form. And continue. And we try to also to characterize the distribution of the new geometric standard power function, and we are able to obtain the first and the second moments to be as given in the slide. And with the first and second moments, we can also obtain a variance of x. Now we went further to obtain the probability generating function. Probability generating function is also very, very important in characterizing distribution, and we can recover the distribution of the various values of x. We obtain the probability generating function, and the probability generating function is expressed as a hypergeometric function given by equation 6. And using a method of a maximum likelihood approach, now we can obtain the log likelihood function of equation 4. That's the new PDF of a new distribution as equation 7. And this is not linear. And in other words, if you are trying to estimate the parameter of theta, you may not able to have a closed form of that, but we can obtain the its estimates by using other optimization technique, which can be found in so many statistical softwares. Now, however, you know what for us to make the program follows a standard power function distribution. So in other words, that will be regarded as our prior distribution. So we can also try to recover the probability of a P given our x. And the prior distribution is seen as which has a structure of a beta distribution given by equation 8. And the mean of the posterior distribution is given as equation 9, which indicates that the mean of the posterior distribution is higher than the prior distribution. And another important remark about this new distribution is that the variance of the new distribution is greater than its mean. In other words, it is very, very good in modeling over dispersed data. So thank you very much. Yeah. In terms of application, it's still ongoing. Somebody was convolution. Yeah, in convolution, we are trying to equate a random variable that has a different distribution together as the other one. In other words, if you have x, y, z, you can convolute x as x equals z minus y, and then you derive the distribution. But in this case, you are trying to make a probability statement about a parameter of a certain distribution.
Okay, so it's okay. So, Dr. Bidemi, you heard that in this case, he's trying to just make one or two adjustments on how the data at hand can fit into the new distribution. Thank you very much. Any other question? Yes, Prof, sir. Take.
Your likelihood, the function you presented, likelihood function.
Go
What
back.
were you, what are you going to do with it? You didn't just left it alone and jump. So I'm surprised with that jump. Go to that hand. Come back.
Go back.
Yes.
No,
No.
front.
Up. Yes. Here, just what did you say? I don't close form solutions.
Yeah, it's a non-linear. Looking at it, it's a non-linear equation, and for us to obtain the estimator of yes,
This equation on its own, you must do something before you try to do something. We're not going to differentiate.
that's what I'm saying.
Yeah, you just presented it. You should have either you tell us or you just and you jump again. Let's leave this one. Come slide down. Let's see. Go to the next slide. What are you now doing here again?
This is the posterior. This is the posterior
Why
distribution.
posterior? What are you looking for? Why are you doing
Posterior is because we made a parallel.
It's okay. What
Parameter of the distribution to follow standard power function.
I was thinking, you will not go Bayesian. That is the idea.
It's a Bayesian.
But maybe something was wrong with your likelihood.
No.
But
For you to derive posterior,
yes, where I didn't see it. That's what I'm asking. Although I came late, no, I apologize. I came late. It's so
what I presented here, I used the results.
okay.
If I didn't do the Bayesian, I wouldn't have gotten this equation.
It's okay. But in any case, that equation 7, you should also do it properly. You differentiate and is that result that you will. That's okay, huh? Where is the
But now when we're making conclusion, may not be that are dispersed. That this assists us a lot.
Is a yeah. Okay. Well, that's it.
Thank you very much for coming, and thank you very much for sorry. Thank you very much for coming. Thank you very much for being very patient with theory. That's how theory is. Those who want to see practical maybe applying it in market survey. But I want to appeal to all of us that gave this kind of work, see how it can be applied, so that those of us who are working in the trading industry or who want to also be a statistician will know why this kind of presentation will be useful to us. I really want to thank you, and I want to thank the Cison executive and the council members who felt that we should head the theory session. Thank you very much, and God bless all of us. So we must make sure you also step out for the have to start to come back. Yeah.
You unplugged your this one.
You never finish.
Okay, you open here. When on the clear now, don't worry. Open. Open. I just open. I'm saying I know. What's your phone? You feel off, make I stop, make I end it.
Contract on your call.
In fact, I end the ceremony.